Electrophilic aromatic substitution is where we add substituents to this ring in an electrophilic manner. I'll make another video about that mechanism. For right here, I'm going to focus on the directing groups. So there's three main types of directing groups, okay? And these groups direct where on the ring your new substituent will add. And there's three positions you need to know, first off. There's the ortho positions right here, which is the 2 and 5 position, 2 and 6 position respectively to your group. Then there's the meta position, which is 3 and 5 respectively to your group, and the para position, which is the 4 position respectively to your group. Electron drawing groups are what's known as ortho para directors, and conversely, electron donating groups are what's known as meta directors. Actually, I just realized I messed that up. Never mind. Those are backwards. Electron withdrawing groups are meta. Electron donating are ortho para. And we'll go over that in a second. As the name implies, electron withdrawing groups remove electron density from the ring. This deactivates it towards electrophilic aromatic substitution. So not only are they meta-directing, they are deactivating. Say it right, deact. Electron donating groups, conversely, as the name implies, donate electron density into the ring. They're going to give it some juice. They're going to prime it for electrophilic aromatic substitution, making that ring much more reactive. So these are activating. And like anything in organic chemistry, there's exceptions to the rules, which would be our halogens. So halogens are ortho para directors, which might make you think, why aren't they with the electron donating groups? Well, it's because they aren't electron donating. They sort of are in there. They're deactivating to the ring. I don't know if I spelled it right, but anyway, they're deactivating to the ring, but they're ortho para directors, and we'll go over that later in the video. So while they do add to the ortho para position, they deactivate the ring, making it less reactive. Let's start with the electron donating groups first. So we know these add at our ortho and para positions. So we have electron donating group. And electron donating groups are typically things that have lone pairs in them. Think of an alcohol, a methoxy group, so like phenol, anisole, or just methoxybenzene, stuff like that. Those are going to donate down into your ring. So there's two ways to think about it. The way I was taught to think about it was, let's use phenol as our example. Phenol has two lone pairs. We're going to inject that electron density into the ring. So let's push it into the ring here. Now, when we do this, we have to remove this double bond because we can't have 5 bonds on a carbon. So we're going to put it up here. What does that give us? That gives us something that looks like this, where now we have a negative charge on this carbon right here because of that lone pair, and a positive charge on our oxygen. Now we can move this around again to down here, but we're going to have to move this. So we move this up here, where we can do here, I'll put it over here, do something similar, where this is positive. We now have double bonds on either side, a negative charge at the para position. So there's extra electron density here. We can just go one more step further, push this here. We push these back up here. And we essentially created this, but flipped back at the para position again. So what you come up with is that there's just this ortho, and these two ortho and these para positions are just extra juiced. That's how I like to think of it. Now, some professors may teach it not in that way, but that when you have the addition, so we have the electrophilic substitution, say at this ortho position, say we add it right there, that ortho position. Actually, not going to do it at that position. I might. Yeah, I'm going to do it that one. No, this one, I'm sorry. So we do it at this ortho position, where we have our alcohol, and I'm just gonna write as E, electrophile. Now, what do we do when we generate that? We generate a carbocation right there in our structure. So now what can we do? This is where we can push the electron density into here, and we get this. This is especially stable. And that's why we can do that. Similarly, if we go at the para position, so we go right here. Again, we're just going to use E. We've generated a carbocation right there. What we can do is push our electrons back down and push this bond over. Once again, putting a partial positive right there, making this, oh, I'm sorry, no, there's not one there, exceptionally stable in terms of its resonance form. However, for the meta, we can't really get away with that. So let's pretend we did meta attack right here. Yeah. We can push this bond around, but it's only going to put the carbocation in there. And we can't push, I should have used my eraser, oh well. We can't push these electrons down, it's still there. Then we have 5 bonds on that carbon. There's just nothing that we can do to get this to a position where it's stable. We can put, all we can do is push this around, this carbocation around at to the ortho and para positions. So this makes this addition much less stable, which is why these go to the ortho and para positions just so much more. Let's go to our electron withdrawing groups. Now, electron withdrawing groups, like I said, as the name implies, they withdraw electrons from the ring. And these are things typically that have pi bonds in them. So think carbonyls. If that carbonyl is attached to the ring from an ester, carboxylic acid, or an amide, NH2, those are electron withdrawing, or even a nitrile. It's going to pull electron density out of the ring. Now, there are 2 exceptions to this. If the amide and the ester are connected by the oxygen or the nitrogen, those are actually weakly electron donating. Generally, your professor won't try to trip you up like that, but just know about it. So, why do these prefer the meta position? And it's not so much these prefer the meta position. They're not so much meta directors as they are ortho power avoiders, or some people say meta allowers. So let's work this with, we'll do it with benzoic acid. It's easy. So we're going to pull electron density up into this ring. Okay, we're going to pull it up. We were like, give me that. Okay, we're going to pull electron density up, and then we're going to push it up here. So what does that give us? Where we have this and this right here. We have a carbocation at our ortho position. Okay, that's no bueno. Now, what do we do if we want to push it around? We can push this around, but if we push it there, this just simply, what do? We move the bond here, move the carbocation to the para position. So what we do is we extremely deactivate these ortho and para positions. So the ring overall is deactivated, but those positions especially are just incredibly deactivated. Now, let's go to our halogens. As I said before, the halogens withdraw electron density out of the ring. This bond is extremely polar. It's just pulling so much electron density out of that ring, it is deactivating to the ring. However, because it does have these non-bonding lone pairs, they can be donated back into the ring in a somewhat similar sense to the electron donating groups. And so that's why it's stabilized. And that's what makes it this exception. So where it's that ortho para director, but it is a deactivating to the ring. So those are your main takeaways. So electron donating groups, those activate and they're ortho para. I don't know why I keep trying to make that an R. Electron withdrawing, those are meta and deactivating. Halogens, ortho para, deactivating. And if you like this and you want more organic chemistry content, be sure to hit that follow button.